Some equations cannot be solved exactly with algebra. This is how you close in on the answer anyway, and already on screen is a curve that no amount of rearranging will ever solve cleanly. Here is that function, f of x equals x cubed minus x minus 1. We plot it so we can see where it crosses 0. Check f of 1, that gives minus 1, which is negative. Check f of 2, that gives 5, which is positive. Because the function is continuous and it goes from negative to positive, a root must sit somewhere inside that interval. We shade the region between 1 and 2 to mark it. Now let's view that same curve and shaded interval from a tilted three-dimensional angle just to see the shape of the crossing more clearly, before we go back to the flat view to work in. Interval bisection uses that sign change directly. Take the midpoint of 1 and 2, which is 1.5, and check the sign of f there. f of 1.5 comes out positive, so the root must be in the left half, between 1 and 1.5. We discard the other half completely. Halve again. The midpoint of 1 and 1.5 is 1.25. Evaluate the sign there, and keep whichever half still shows the sign change. Repeat that one more time. Each halving squeezes the interval tighter around the root, and after just 3 or 4 steps, the interval is already small enough to pin the root down accurately. Fixed point iteration takes a different approach. Rearrange x cubed minus x minus 1 equals 0 into the form x equals g of x. For example, x equals the cube root of the quantity x plus 1. Now feed a starting guess into that rearrangement, take the output, and feed it back in again and again. Plotted as a cobweb diagram, the path bounces between the curve y equals g of x and the straight line y equals x. Watch the staircase of lines drawn between those two graphs. Each bounce lands closer to the point where the curve meets the line, and that meeting point is exactly the root we are chasing. Not every rearrangement behaves so well. Here is one rearrangement whose cobweb spirals inward, converging steadily toward the root shown on the left. And here, cleared and shown fresh, is a different rearrangement of the very same equation. Its cobweb spirals outward, moving further from the root with every step, which means it diverges. The equation is identical in both cases. Only the choice of rearrangement decides whether the iteration converges or diverges, so that choice really matters. Newton-Raphson converges fastest of all. Start with a guess and draw the tangent line to the curve at that point. Follow that tangent line down to where it crosses the x-axis. That crossing point becomes your new, much better guess. Draw the next tangent at this new guess and again follow it down to the x-axis. Each step, replacing the last tangent line on screen, lands dramatically closer to the true root. After just 2 or 3 of these steps, the guess has already locked onto an accurate value for the root, far faster than bisection or basic fixed point iteration. Full process. Step 1. Find 2 x values where the function changes sign. Step 2. For bisection, repeatedly halve the interval, keeping the half with the sign change. Step 3. For fixed point iteration, rearrange into x equals g of x and iterate, checking the cobweb converges. Step 4. For Newton-Raphson, repeatedly follow the tangent line down to the x-axis for a faster next guess. Watch out! The single biggest mistake is picking a rearrangement for fixed point iteration without checking whether its cobweb actually converges, since some rearrangements of the exact same equation will diverge instead. Simplified version. A sign change between 2 points guarantees a root between them. Bisection halves the interval repeatedly. Fixed point iteration rearranges into x equals g of x and checks convergence with a cobweb. Newton-Raphson follows tangent lines to the axis for the fastest convergence.